Brought to you by WikiVidi.com. False vacuum. In quantum field theory, a false vacuum is a vacuum which exists at a local minimum of energy, and is therefore not truly stable. This is in contrast to a true vacuum which exists at a global minimum and is stable. A false vacuum may be very long-lived or metastable. True versus false vacuum. A vacuum state is defined as a space with as little energy in it as possible. Despite the name, the vacuum state still has quantum fields. A true vacuum is a global minimum of energy and coincides with a local vacuum. This configuration is stable. It is possible that the process of removing as much energy and particles as possible from a normal space results in a different configuration of quantum fields with a local minimum of energy. This local minimum is called the false vacuum. In this case, there would be a barrier to entering the true vacuum. Perhaps the barrier is so high that it has never yet been overcome anywhere in the universe. A false vacuum is unstable due to the quantum tunneling of instantons to lower energy states. Tunneling can be caused by quantum fluctuations or the creation of high-energy particles. The false vacuum is a local minimum but not the lowest energy state. Standard model vacuum. If the standard model is correct, the particles and forces we observe in our universe exist as they do because of underlying quantum fields. Quantum fields can have states of differing stability, including stable, unstable, or metastable. If a more stable vacuum state were able to arise, then existing particles and forces would no longer arise as they do in the universe's present state. Different particles or forces would arise from whatever new quantum states arose. The world we know depends upon these particles and forces, so if this happened, everything around us, from subatomic particles to galaxies and all fundamental forces, would be reconstituted into new fundamental particles and forces and structures. The universe would lose all of its present structures and become inhabited by new ones based upon the same quantum fields. Stability and instability of the vacuum. Many scientific models of the universe have included the possibility that it exists as a long-lived but not completely stable sector of space which could potentially at some time be destroyed upon toppling into a more stable vacuum state. A universe in a false vacuum state allows for the formation of a bubble of more stable, true vacuum at any time or place. This bubble expands outward at the speed of light. The standard model of particle physics opens the possibility of calculating, from the masses of the Higgs boson and the top quark, whether the universe's present electroweak vacuum state is likely to be stable or merely long-lived. A Higgs mass seems to be extremely close to the boundary for stability. However, a definitive answer requires much more precise measurements of the top quark's pole mass, and new physics beyond the standard model of particle physics could drastically change this picture. Existential threat. In a 2005 paper published in Nature as part of their investigation into global catastrophic risks, MIT physicist Max Tegmark and Oxford philosopher Nick Bostrom calculate the natural risks of the destruction of the Earth at less than 1 per giga-year from all events, including a transition to a lower vacuum state. They argue that due to observer selection effects, we might underestimate the chances of being destroyed by vacuum decay, because any information about this event would reach us only at the instant when we too were destroyed. This is in contrast to events like risks from impacts, gamma-ray bursts, supernovae and hypernovae, whose frequencies we have adequate direct measures of. If measurements of these particles suggest that our universe lies within a false vacuum of this kind, then it would imply, more than likely in many billions of years, that it could cease to exist as we know it if a true vacuum happened to nucleate. In a study posted on the Arxiv in March 2015, it was pointed out that the vacuum decay rate could be vastly increased in the vicinity of black holes, which would serve as a nucleation seed. According to this study, a potentially catastrophic vacuum decay could be triggered any time by primordial black holes should they exist. If particle collisions produce mini black holes, then energetic collisions such as the ones produced in the LHC could trigger such a vacuum decay event. However, the authors say that this is not a reason to expect the universe to collapse, because if such mini black holes can be created in collisions, they would also be created in the much more energetic collisions of cosmic radiation particles with planetary surfaces. And if there are primordial mini black holes, they should have triggered the vacuum decay long ago. Rather, they see their calculations as evidence that there must be something else preventing vacuum decay. Inflation. It would also have implications for other aspects of physics, and would suggest that the Higgs self-coupling lambda and its beta-lambda function could be very close to zero at the Planck scale, with intriguing implications including for theories of gravity and Higgs-based inflation. A future electron-positron collider would be able to provide the precise measurements of the top quark needed for such calculations. Vacuum metastability event. A hypothetical vacuum metastability event would be theoretically possible if our universe were part of a metastable vacuum in the first place, an issue that was highly theoretical and far from resolved in 1982. A false vacuum is one that appears stable, and is stable within certain limits and conditions, but is capable of being disrupted and entering a different state which is more stable. If this were the case, a bubble of lower energy vacuum could come to exist by chance or otherwise in our universe, and catalyze the conversion of our universe to a lower energy state in a volume expanding at nearly the speed of light, destroying all of the observable universe without forewarning. Chaotic inflation theory suggests that the universe may be in either a false vacuum or a true vacuum state. A paper by Coleman and De Lucia, which attempted to include simple gravitational assumptions into these theories, noted that if this was an accurate representation of nature, then the resulting universe inside the bubble in such a case would appear to be extremely unstable, and would almost immediately collapse. Such an event would be one possible doomsday event. It was used as a plot device in a science fiction story in 1988 by Jeffrey A. Landis, in 2000 by Stephen Baxter, and in 2015 by Alistair Reynolds in his novel Poseidon's Wake. In theory, either high enough energy concentrations or random chance could trigger the tunneling needed to set this event in motion. However, an immense number of ultra-high energy particles and events have occurred in the history of our universe, dwarfing by many orders of magnitude any events at human disposal. Hutt and Rees note that because we have observed cosmic ray collisions at much higher energies than those produced in terrestrial particle accelerators, these experiments should not, at least for the foreseeable future, pose a threat to our current vacuum. Particle accelerators have reached energies of only approximately 8 tera-electron volts. Cosmic ray collisions have been observed at and beyond energies of 1018 electron volts. A million times more powerful, the so-called Greisen-Zatz-Eppen-Kosman limit. And other cosmic events may be more powerful yet. Against this, John Leslie has argued that if present trends continue, particle accelerators will exceed the energy given off in naturally occurring cosmic ray collisions by the year 2150. Fears of this kind were raised by critics of both the relativistic heavy ion collider and the Large Hadron Collider. at the time of their respective proposal and determined to be unfounded by scientific inquiry. Bubble nucleation. In the theoretical physics of the false vacuum, the system moves to a lower energy state, either the true vacuum or another lower energy vacuum, through a process known as bubble nucleation. In this instant, effects cause a bubble to appear in which fields have their true vacuum values inside. Therefore, the interior of the bubble has a lower energy. The walls of the bubble have a surface tension as energy is expended as the fields roll over the potential barrier to the lower energy vacuum. The most likely size of the bubble is determined in the semi-classical approximation to be such that the bubble has zero total change in the energy. The decrease in energy by the true vacuum in the interior is compensated by the tension of the walls. Joseph Lukin has said that study of the exact properties of the Higgs boson could shed light on the possibility of vacuum collapse. Expansion of bubble. Any increase in size of the bubble will decrease its potential energy, as the energy of the wall increases as the surface area of a sphere 4 pi r squared. But the negative contribution of the interior increases more quickly, as the volume of a sphere, text style, frac pi r cubed. Therefore, after the bubble is nucleated, it quickly begins expanding at very nearly the speed of light. The excess energy contributes to the very large kinetic energy of the walls. If two bubbles are nucleated, and they eventually collide, it is thought that particle production would occur. Where the walls collide, the tunneling rate is increased by increasing the energy difference between the two vacua and decreased by increasing the height or width of the barrier. Gravitational effects. The addition of gravity to the story leads to a considerably richer variety of phenomena. The key insight is that a false vacuum with positive potential energy density is a de Sitter vacuum, in which the potential energy acts as a cosmological constant, and the universe is undergoing the exponential expansion of de Sitter space. This leads to a number of interesting effects first studied by Coleman and de Lucia. Development of theories. Alan Guth, in his original proposal for cosmic inflation, proposed that inflation could end through quantum mechanical bubble nucleation of the sort described above. See History of chaotic inflation theory. It was soon understood that a homogeneous and isotropic universe could not be preserved through the violent tunneling process. This led André Linde and independently Andreas Albrecht and Paul Steinhardt to propose new inflation, a slow-roll inflation in which no tunneling occurs, and the inflationary scalar field instead rolls down a gentle slope. Brought to you by WikiVidi.com. Would you like to know more?